Okay, let's talk synchros. I know. The name itself can sound a little intimidating, especially with an exam just around the corner. But trust me, the core idea behind them is actually super clever and not nearly as complicated as you might think. We're going to break it all down, piece by piece, so by the end of this, you'll be more than ready for that test. So, let's just dive right in.
So here's our game plan. First, what the heck is a synchro? Then, we'll crack one open and see what's inside. We'll look at the two big jobs they do, meet the key players in the synchro family, and then put it all together to see how a simple system works. And yeah, we'll wrap up with a super fast recap and a few questions to lock it all in. Sound good? Let's go.
All right, Section 1. What is a synchro? Let's get right to the big idea.
Okay, so here's the textbook definition. It's a rotary electromechanical position sensing device. Well, that's a mouthful, right? But don't let it throw you. The key phrase here is position sensing. All a synchro really does is sense the angle of something and then send that information somewhere else. Think about it. How does a captain on a huge ship turn a wheel up on the bridge and make the rudder, way back at the stern, turn to the exact same angle? That's what a synchro does. It transmits that angular information super accurately and super fast.
You know what? The absolute best way to think about this is to call it an electrical drive shaft. A regular drive shaft, right? It's a solid piece of metal. It connects an engine to the wheels. It's rigid. It's direct. A synchro does the exact same thing, but instead of a big metal rod, it uses a few simple wires. And that's a total game changer, because it means you can link two things together perfectly, even if they're miles apart.
And this picture right here, this shows it all perfectly. Look at the left. Someone turns that hand wheel. That's your mechanical movement. The first synchro, the transmitter, takes that spin and turns it into a special electrical signal. That signal zips through the wires over to the other synchros, the receivers. And what do? They take that electrical signal and turn it back into the exact same mechanical spin, moving those two dials. It's like magic, right? Motion in one place is perfectly mirrored somewhere else.
Okay, so now that we get the what, let's look at the how. We need to pop the hood and look at the two main parts that make this whole thing work. First, we've got the rotor. And just like the name says, it's the part that rotates. This is the piece that's physically connected to whatever you're turning, like that hand wheel. You feed it some AC voltage and boom, it becomes an electromagnet. So as you turn the rotor, you're also turning its magnetic field. Basically, this is the part that sends the position. And they come in two main shapes. The one on the left, that's called a salient pole rotor. Kind of looks like a dumbbell, right? That's what you'll find in most of the basic units. The one on the right is a drum rotor. It's a bit more complex, and you see it in systems where you need a lot more precision.
Now, for every rotor, there has to be a stator, and this is the other half of the magic. The stator is stationary. It stays put. It's basically a hollow cylinder with three sets of wires or windings inside, and they're arranged in this special Y shape, exactly 120 degrees apart from each other. Its whole job is to just sit there and listen to the magnetic field that the spinning rotor is creating.
And here's how they fit together. The rotor just spins right inside the stator. Now this is the really cool part. As that rotor's magnetic field spins, it passes by those three stator windings. Depending on the rotor's exact angle, it's going to induce a different amount of voltage in each of those three windings. So for any given angle, you get this unique combination of three voltages. It's literally an electrical fingerprint that represents that precise physical position. That's the secret sauce.
Okay, so we know a synchro can turn an angle into an electrical fingerprint. So what do we do with it? Well, there are basically two different jobs these systems are built for.
Now this is super important, especially for an exam. You've got two main types. First, there are torque synchros. Think light loads. These are the ones that do the actual work themselves. They provide the physical turning force, the torque, to move something small, like a needle on a dial. Easy enough. But what if you need to move something massive, like a huge radar antenna or a gun turret? A tiny synchro can't do that. That's where control synchros come in. They're the smart ones. They don't try to move the heavy thing directly. Instead, they just create a tiny little error signal that bosses around a big, powerful motor system. It's like they're whispering, hey, you're off by 2 degrees to the left. Fix it. So, torque for small stuff, control for big stuff.
So within those two systems, you've got a few different kinds of synchros, each with a specific role. Let's meet the main players in the family. Okay, here are the abbreviations you're going to see. For those simple torque systems, you've got a TX, a torque transmitter, and a TR, a torque receiver. The TX sends the signal, the TR receives it and moves. Simple.
For the heavy-duty control systems, it's a CX, a controlled transmitter, and a CT, a controlled transformer. That CT is the brains of the operation. It's the one that creates that error signal. Now, for your exam, you absolutely need to know the basic pair, the TX and TR, so let's focus on how they work together.
All right, let's put it all together. How does this simple TX and TR system actually work? Let's see it in action.
It's really just a three-step dance. Step 1. Everything is perfectly lined up. The transmitter's rotor and the receiver's rotor are at the exact same angle. The system is balanced and no electricity is flowing. This happy, stable state has a name. It's called correspondence. Step 2. Someone turns the knob on the transmitter. Uh-oh, now the rotors don't match. The whole system is electrically unbalanced. Step 3. Because it's unbalanced, current starts to flow. This creates a magnetic force inside the receiver that physically twists its rotor, forcing it to follow and catch up to the transmitter. As soon as it matches the transmitter's new position, everything is balanced again, the current stops, and the system is back in correspondence. It's constantly trying to find that balance.
And this diagram shows that story perfectly. See diagram A? The rotors match. Everything is in correspondence, a state of perfect balance. No current is flowing, it's just sitting there. Now look at B. The transmitter on the left has been turned. They're out of sync. This creates that imbalance, and you can see current starts to flow from one stator to the other. And in C, that current has created a magnetic force that literally drags the receiver's rotor around until it catches up. Once they match again, boom, we're back in correspondence and the current stops. The receiver will always follow the transmitter.
Okay, that's the whole process. We went from the big idea all the way down to the nuts and bolts. Let's do a quick recap to drill these ideas into your brain before a little quiz.
Ready? Rapid-fire recap. Synchro, it's an electrical drive shaft for angles. Rotor, the spinning part. Stator, the part that stays still. Torque system for moving light stuff like pointers. Control system for bossing around motors to move heavy stuff. Transmitter, TX, it sends the angle. Receiver, TR, it follows the angle. And correspondence, that's a happy place where everything is perfectly aligned and balanced. Got it?
All right, let's see what you've learned. Hit pause after I read these and see if you can answer them out loud. First, what's the #1 job of a synchro system? Second, what are the two main parts inside every synchro? Third, what's the big difference between a torque system and a control system? Fourth, in that basic TX-TR pair, what does the transmitter do? Fifth, what about the receiver? What's its job? And last one, what do we mean when we say a system is in correspondence? If you can nail those, you're golden for your exam.
So, we'll leave you with this final thought. Now that you know how this works, how you can turn one dial and have another one follow it perfectly from miles away, start thinking about where else you see this. Because this basic idea, this principle of electrical correspondence, it's not just for old-school shiprunners. It's a foundational concept in robotics, in automated manufacturing, in aerospace, pretty much anywhere you need precise remote control. It all comes back to this incredibly elegant idea. Thanks so much for joining me, and seriously, good luck on that exam.